Okay, so what we are doing today is starting on the symmetric group, and I said we'll start to look at the symmetric group in detail. So there's this really beautiful paper called A New Approach to the Representation Theory of Symmetric Groups. And there's two versions of this paper, and it's by Akunkov and Vershik. And in one version, it's Akunkov-Vershik, in the other version, it's Vershik-Akunkov. So I'm not sure which order the authors should be in. It's a very remarkable and beautiful paper from 1996. And somehow it really changed the way that we look at the representation theory of symmetric groups. I think it gave us a new way of looking at this representation theory, which I think in hindsight has been incredibly fruitful.
Let me just add that there's also a book on the Akunkov-Vershik approach, which gives a few more details if people want to.
The Kleshnev one?
I don't remember the name, but it says Akunkov-Vershik in the title. So it should be too difficult to find on Russian sites and then download.
So I want to explain this in some detail. And before I explain it in some detail, I want to explain it in a very broad overview. And before I explain it in very broad overview, I want to give some very quick historical context. So here's Rep-SN. And in my opinion, there's four different ways of looking at its representation. So there's the original way, which is basically Schur functions and connections to GLN. And this is Frobenius and Schur around about 1900. Okay, so Frobenius wrote down the character table of the symmetric group in 1900, and he did it essentially by bringing in a whole lot of symmetric functions. And then we have Young modules, Specht modules. So basically, this is very much characters. Here we write down the characters of the symmetric group. Okay. We have Young modules, Specht modules. And this is Young, and I think around about 1930 or something. So my understanding is he's an English pastor, very interested in representations of symmetric groups. And this is typically the way that you will learn this in a first subject on symmetric groups. So what people will say is you take your symmetric group, you have a partition, you do some induction of the trivial representation, you do another induction of the sign representation, and there's a unique common constituent, and you can write down this constituent with some combinatorics. It's called a Specht module, and you can start studying it. Okay? And it's very explicit, and it really just stays in SN. Now we have the Akunkov-Vershik approach.
So, Geordie, would you say that the first approach on that list could be basically like take Schur-Weil duality as a definition? Or like if you knew that theorem, then just use that to give the Erops of SN? Or would that be more the second approach?
Yeah, so in my rough understanding, the history is that Frobenius first did this kind of using symmetric functions and did the case of symmetric groups. And then he said to his fantastic student, Ishai Schur, it looks like you could get to GLN, and also maybe it's easier once you've done GLN to go back to symmetric groups. And that's what Schur did in around about 1910. And you have Schur-Weil duality and okay. So the connection, that's that package. But I don't have it very clearly in my head at the moment. But roughly, there's a cloud of ideas there. There's the Akunkov-Vershik approach, which is today. So this is today. And then there's another beautiful approach, which is in my head linked with Zelavinsky and Bernstein, which is a big Hopf algebra. So basically, what they do is they take the direct sum of all the Grothendieck groups of all representations of symmetric groups, and then say this has a multiplication and a co-multiplication. It's a Hopf algebra, a very nice form. And then they say This is so nice that we can in fact entirely describe this top algebra, and you get all the links to symmetric functions and all that kind of stuff. Okay, and this is something incredibly elegant, but it's one of those things that sometimes happens with very elegant machines, that they get exactly what they're designed to give and nothing more. So like if you ask a little bit further, like what about this? It's like, sorry, my machine is perfectly built for the task at hand, but for nothing more. Whereas this Akunov-Vershik approach is incredibly generative in terms of its ideas. Joseph.
What's the identity in that big growth and big ring?
The trivial representation of S1.
So how are they backward compatible? Are you just like you're using the embedding of Sn inside of Sn plus 1 in all this?
Yeah, so to multiply, I do something very funny, which is I take a representation of Sn, I take another of Sn, I put them together, regard them as a representation of I regard them as a representation of Sm times Sn, yes, and then I induce up to Sm plus n. That's my multiplication. And obviously, if you take the
No, you take it to 0. This is why you take it to 0.
yeah, that's why you take it to 0.
Otherwise,
Yeah.
those ones too.
Yeah, that's right.
Wait, isn't it Sn cross Sm sitting inside Sn plus n?
Isn't that what I said?
Oh, okay, yeah.
Okay. So that's the high level overview. Now we get the high level overview of Akunov-Vershik.
So just another question about this high level overview. If you wanted to do things for GLNFQ,
Yes.
I know that the last approach also works in the sense that you just get a number of copies of the big Hopf algebra and you're
Yes.
stoked.
Yes.
Do any of the other approaches, because is the first approach sort of how Green originally did reps of GLNFQ?
My understanding of Green is he worked incredibly hard
Okay.
and got the answer, and everyone was amazed.
Uh-huh.
Green, sorry, I don't know.
So Green worked out the character table of GLNF. So this is GLNC.
Oh, okay.
Green, who somehow is featured a lot in this course, worked out the character table of this group in 1954 or something, and everyone was very impressed.
Still am.
To this day.
And I think, yeah, it's still very impressive. Yeah. It's really it's a very beautiful paper and very remarkable kind of like intense calculations that all work out perfectly at the end.
I think the first approach actually doesn't work because the Chauval duality is not surjective for the finite group.
Yeah, I
So
think
this
that
kind of
just
breaks a little bit apart.
This totally breaks.
Yeah, that's right.
This totally breaks.
That's right.
Yeah, so this works for this works reasonably well for GLNFQ. It also works well for p-adic group, for p-adic GLN, and that's why Bernstein was interested in it. And this somehow is really like, I mean, this plus the work of other people has really created a kind of new paradigm in many of these questions. So
That's right.
it's kind of the most powerful method going forward. Okay, so Akunov-Vershik. So I just want to, before I'll go over here for Akunov-Vershik, and I just want to remind you about some basic facts. So I want to give this lecture in a kind of two-personality way. So the first personality is someone who really knows representation theory of symmetric groups and wants to have a new point of view on it. Okay, and that's the way that the world met Akunov-Vershik. They know at the end partitions are going to come out, standard tableau are going to come out, etc. And it's kind of like a mystery where you know who did it, and you're just trying to work out like what the clues are along the way as you're reading the paper. Yeah. That's the first way. But the second way I want to emphasize is that you can get everything about symmetric groups out of this approach. So even though I'm saying these are basic facts, if you read Akunov-Vershik, it's just all there. Okay, so I really want to emphasize that I'm not kind of, even though it looks like I'm assuming stuff about that we already know about symmetric groups, in fact, one doesn't need to. And I find that like really beautiful. It's really possible just to read from the first page, go through Akunov-Vershik, and you get everything at the end. So the basic facts are that rep Sn is irreducible representations over C of Sn are in bijection with partitions lambda of n. This is the notation for lambda is partition F. So this is canonical. Okay, you might say to me, oh, I know irreducible representations are accounted by conjugacy classes. Conjugacy classes are cycle types, cycle types of partitions. Therefore, I have a bijection between partitions and representations. No, wrong. Yeah, conjugacy classes are not in canonical bijection with representation. They just happen to have the same number. It's like a dual thing. But this is a case where we actually have a canonical association of a partition to an irreducible representation. First basic. Second basic fact is that the dimension, so if we have lambda here, I go across to V lambda here. The second basic fact is that the dimension of V lambda is the number of standard young tableau. Now, please, I ask a question without any obligation, like I don't want anyone to feel any embarrassment. Does anybody not know what a standard tableau is? Okay. So here's a partition, and I will stick to so this is the partition 3, 2 of 5. Okay, so I list the parts in descending order, draw this nice box diagram. Standard tableau means I put entries, so standard tableau is I put entries, so this is called the Young diagram, after our friend over there. Entries 1 to n in the boxes of Young diagram ascending along rows and down columns. Okay, so here's an example. Here's another example. This is not allowed.